4 is belonging to this magnetic material. So under material science, as we know, magnetic materials, I think going to read about magnetic material. These are the following things we are going to learn. That is a classification of magnetic material and BH code for ferromagnetic material. Then we will learn what is a hard and soft magnetic material and their applications. Okay, so these parts whatever is written over here, that thing is already taught you in physics. So before going to enter to the direct classification of magnetic material, first we will recall what you have learned in physics of this year. I think sir have said the PDF in which all the materials related to this particular topics are there. So I'm just going to uh, quickly clear that one because that is already taught in physics. So I'm not going to give much emphasis on all. Okay. So before going to learn about the classification of material, we should remember what is magnetic dipole and what is magnetic dipole moment. Okay, whenever we are considering any material like your, as you can say, um, atomic arrangement. Okay, Bohr's atomic model we know. In that one, we know that the electrons are arranged around the positive nucleus. Okay, positive charge nucleus. The electrons are arranged in the specific orbit, and in the specific orbit they are revolving around the positive ion, as well as they are having a revolution, or we can say they are spinning around their own axis. Clear? So when they are spinning their own about around their own axis and revolving around the positive ion, at that time they are creating this magnetic dipole moment. Okay, magnetic dipole moment, we can say it is the magnetic dipole multiplied by the distance. Okay, distance between the two poles is known as your magnetic dipole moment. Okay, so that is already you people know from physics. So then we can say that magnetic dipole moment already you recall, magnetic dipole you recall. Then comes a magnetic permeability. So magnetic permeability means the material, it is a property of the material which will allow the magnetic lines or magnetic induced magnetic field. Means the if you will place a material in a magnetic field, then that magnetic this material will allow that magnetic field to pass through it. That is what is your magnetic permeability. So for magnetic permeability we have this formula, that B by H, where B is nothing but your magnetic induction and H is the magnetic intensity. Okay, so if we will compare the magnetic permeability of a material in a particular medium and in vacuum, then that will be called as your relative permeability. Relative permeability is a permeability we are calculating to a reference. Okay, always whenever relative term comes, that means there is a reference, and that reference we always take is the vacuum, because vacuum doesn't affect the property that much. So that is why it is your relative magnetic permeability. Next comes your magnetic induction. So when you are going to place a material in a magnetic field, the experience by material is called as magnetic induction, and this is also you have in your college, school and college. Also here also you learn that one. So just for overall idea, I am just telling this one. Then magnetic intensity. Okay, magnetic intensity means that it is the required amount of magnetic amount of magnetic field to create magnetization. Okay, the magnetism which we want to create, that is called as we are representing with them. But to create that, how much magnet intensity is necessary, that is your H. Okay, so this is a relationship between your intensity of magnetic and magnetization. Okay, then comes your magnetic susceptibility. Already I have told you about this magnetic susceptibility in I think in few class back, when I was telling you about your superconductivity. Okay, so when I told you about superconductivity, at that time we learned that a perfect diamagnetic material is a superconductor. Okay, there we learned that the psi value, the value of psi will decide whether it is a diamagnetic material or paramagnetic material or a ferromagnetic material, right? And this psi is nothing but the magnetic susceptibility is nothing but the ratio of your magnetization and the required magnetic field intensity. Okay, this relationship already described in your note that is given by physics sir. I took the screenshot from there and attached over here for your uh, for so confused. They both are same in physics. What I'm going to tell you now, both are same only. So that's why the screenshot from the note and I have taken here. Then okay, we are classifying them depending on two things. As I told here, please let me know if you people are not able to if people are not able to see what I am writing, then please let me know that one in the chat box. Okay, now you see, as I told you already, that we are having this relationship between B and H, right? So I can say that the magnetic induction B is equal to mu naught H bar plus mu naught M bar, right? So here if I will write mu naught H bar plus mu naught psi H bar. So already I did given you the relationship between psi and M and H. So I can replace the value of M with this value. So if I do that one, so what I will get, mu naught multiplied by 1 into 1 plus psi into H bar, right? So 1 plus psi is nothing but your relative permeability. That is also this relationship also we saw in previous slide. So that means here the two terms are there, psi and mu r. So here what happens, I can say that the property of magnetic material, or we can say the magnetization of material, will be dependent on mu r and psi. And as they are dependent on these two values, so we can classify the material by using the following type of your consideration. So the first one is your permeability. Okay. So depending upon the relative permeability, we find here that there are three types of material are there. If the value of relative permeability lies less than 1, then it will be your diamagnetic material. If the relative permeability is more than 1, then it is paramagnetic material. If relative permeability is more than 1, then it will be a ferromagnetic material. Similarly, depending on dipole moment or magnetic dipole moment, which I told you the first slide, depending on that, we are having 5 types totally the magnetic materials. Okay, if there is this permanent magnetic dipole moment is absent in any material, then that will be a diamagnetic material. Okay, that means here the dipole moment will be acting opposite to the induced magnetic induction or magnetic field intensity, or the force created due to the external magnetic field, in which direction the force is acting on the material due to the external magnetic field. Opposite to that, the electrons present in the material is going to generate the magnetic intensity, which will cancel out with each other, and there will be no magnetic effect we will find over there. That is what is your diamagnetic material. If that permanent magnetic dipole moment is present, then also depending on the atomic, if the depending on the effect on atomic arrangement of the material, we are having four types of magnetic material. One is paramagnetic material, ferromagnetic material, antiferromagnetic material, and ferrimagnetic material. As I told you, if you are going to present the material or place the material in a particular magnetic field, at that time it is going to affect the atomics, the electron spin in the material, or in the atomic arrangement of the material, and the effect will be shown on the dipole moment, and that dipole moment will decide which type of material is it. Okay. Now you see here the four type of magnetic dipole moments are represented over here. So whenever you place a paramagnetic material in a magnetic field intensity, that will be this will be your we can say, in case of your paramagnetic material, the magnetic dipole moment arrangement is in random direction. Okay, these arrow marks what you see over here, all these arrow marks what you can see, these are your direction of magnetic dipole moment, and the orientation of this magnetic dipole moment is random, but they will be parallel to the external magnetic field. Okay, this is a random arrangement of the magnetic dipole moment. Similarly, in ferromagnetic material, this magnetic dipole moment which will be created due to the external magnetic field will be parallel and in the same direction of the applied magnetic field. So what happened? Let us consider this is a material I am having, and here when I am giving the force, or I am giving an external magnetic field, then what happened in ferromagnetic material? It will be parallel to the magnetic field induction, but it is also going to be in the same direction as well. But in case of diamagnetic material, this is your ferromagnetic material. But in case of diamagnetic material, if I place the material in a magnetic field induction, then the induction will be created opposite to the, or the magnetization will be opposite to the external magnetic field. That's why it will be cancel out with each other, and it is called as a diamagnetic material. So when I am saying this one now, at that time, this magnetic field cannot pass through this material in case of a diamagnetic material. But in case of your paramagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic material, the arrangement will be the magnetization will pass through the material. That's why this difference is created. Okay. Then comes your antiferromagnetic material. So in antiferromagnetic material, there will be two dipole moments will be created. One will be along the external magnetic field parallel to that one and in the same direction like this. Okay, and another one will be opposite to the magnetic field intensity, and this arrangement of these two different direction dipole moment will be alternative. So one will be in the same direction, means one layer will be in the opposite direction. Again, one will be in same direction, means one will be in opposite direction. So alternatively, they are going to be arranged throughout the material. This is your antiferromagnetic material. In case of ferrimagnetic material, this is going to show the same type of arrangement of magnetic dipole moment as in case of your antiferromagnetic material. But the amount of moment created by the same direction dipole moment will be more than the opposite direction moment. Okay, so when you will write all these things now, at that time you have to draw the diagram. There you have to make it clear that these two moment magnitude created either in the same direction and opposite direction are same. But in case of ferrimagnetic material, the amount of the magnitude of the dipole moment will be different. The same direction moment will be more than the opposite direction moment. Okay, that is what is the four dipole moments created in the magnetic material, and depending on that we have segregated this type of four type of magnetic materials. So paramagnetic, ferromagnetic, antiferromagnetic and ferrimagnetic material. If you people have any doubt, you can ask here. Okay, so now if you are okay, some doubt is question message came. That is the because of the one is the property like your the susceptibility, permeability, and another, and that property is dependent on the electron spin. Okay, the electrons that is spinning around the proton and the around their own axis, that will decide which type of behavior they will show. Okay, so that dipole moment, how much dipole moment will be created depending upon their atomic arrangement or Bohr's atomic model and the spin of the electron. Okay, always remember a magnetic property of a material is directly related to the spin of the electron and the revolution of the electron around the nucleus. Okay, so for different material, this dipole moment created will be different. Okay, so that is totally like that particular thing. If you want to learn in deep, then you have to go for mathematical derivations and all. Okay, so as of now, the answer to your question is that depending on the spin of the electron, the property of the material is going to vary, which will decide whether they will be acting as a ferromagnetic material or paramagnetic material or antiferromagnetic material or ferrimagnetic material, or else we can also say that diamagnetic material is well. Okay. Okay. Now we will go for the difference between this in among these five types of material I told you over here. This paramagnetic, ferromagnetic, antiferro, ferrimagnetic, and diamagnetic material. Among these three magnetic materials are most important actually. Okay, I am not representing anything now. Okay, now you can see this diamagnetic, paramagnetic, and ferromagnetic material actually are the most important three types of material we are using. Okay, and this antiferromagnetic and ferrimagnetic, they are having a little use, or in your according to your undergraduate course, this antiferro and ferrimagnetic doesn't hold that much of importance. That's why we will only focus on diamagnetic, paramagnetic, and ferromagnetic material. Okay, first we will see what are the different properties, that is, or the difference we will see actually. Okay, in the difference format we will try to remember what are the different properties of these different type of materials over here. Okay, so first we will be see the ferromagnetic material. Okay, we will compare the ferromagnetic material with paramagnetic and diamagnetic material. As I already told you, there we will find some similar properties between ferromagnetic and paramagnetic material, but diamagnetic material will be little bit different than those of two, because the dipole moment created in diamagnetic material will be opposite to the applied magnetic field. Okay, so we can say that if there is a magnetic field is there, and in that one we are keeping. Okay, I am writing in a difference format. Okay, so I can say that if I will place any material in a magnetic field, the attraction of the material towards the magnetic field will be also showing its property, whether it is a ferromagnetic, paramagnetic, or diamagnetic. Okay, if we place a ferromagnetic material in a magnetic field, then there will be a strong attraction towards the magnetic field we will see in case of a ferromagnetic material. For example, let us consider this is a ferromagnetic material. Initially, these are the magnetic field induction, or magnetic field was there. Now, when we place a ferromagnetic material over there, we will see that this magnetic field is going to be attracted towards this ferromagnetic material, and that will be passing through the material. Okay, this is what is a magnetic field, external magnetic field. And as we place this ferromagnetic material here, they got attracted towards this ferromagnetic material. So this is called as a strong attraction. But if we see a paramagnetic material or a diamagnetic material, this attraction force is very not that much strong. So we call it as a feeble attraction. Okay, so I can say here strong attraction towards. If you cannot read what I am writing, let me know that one also. Okay, I can say strong attraction of strong attraction towards the magnetic field. But in case of paramagnetic, this attraction is feeble. Feeble means weak. Okay, this is a weak attraction. In diamagnetic also, this is weak. Feeble attraction. Right? Then comes your So due to this strong attraction and feeble attraction, the magnetic or field lines, what is the magnetic field we are inducing, that field lines are going to be concentrated at the material, concentrated towards the material, right? The diagram I shown you previously, that is what is called as your concentration of your magnetic field. So as there is fewer attraction, this concentration will be very few. In diamagnetic material, that the magnetic field lines will not be going to be like in diamagnetic material, the inductions are not passing through the material. They will be repelled through from the by the material, and no magnetic field will be passing through it. So in previous class we have seen, in case of your superconductivity, if this is a material placed in the magnetic field, then this magnetic field is not able to pass through the material, and it is going to be repelled by the material and will pass through like this. Okay, this one what was we learned in previous class, right? So this is what is called as your this particular thing we cannot see in case ferromagnetic. In case of ferromagnetic material, these are going to be attracted towards the material, and that is totally opposite to the diamagnetic material, right? This is what we see in case of your ferromagnetic material. This is what we see in case of your diamagnetic material, and we will see in case of paramagnetic material, these are passing through this one. Okay, this is what is the difference. We can say the concentration of the lines. Okay, field lines, the concentration of field lines are attracted towards the material. Here these lines will pass through the material, but in this case it will not pass through the material, rather it is going to be repelled by the material to the outside. So I can write this one. So the field lines are concentrated at the material. In case of ferromagnetic material, concentrated field lines in material. Similarly, here field line will pass through material, but not concentrate as in case of your ferromagnetic material. Okay, but in case of diamagnetic material, it will not pass at all. Okay, or if it is a perfect diamagnetic material, it will not pass at all, or we can say very few lines will pass. These lines, when I am saying, these are the magnetic induction lines, okay, or external magnetic field lines. Pass through material. Okay, the third difference is their susceptibility. Okay, here for a ferromagnetic material, the susceptibility of the material is positive and large. Okay, this will be your positive, and it will have a very large value. But in case of your paramagnetic material, the susceptibility is less than unity but positive. So I can say the susceptibility is less than 1 but positive. Positive means it will be lying between 0 to 1. Okay. So we can say that here susceptibility is more than 0, that means positive, but less than 1. But in case of diamagnetic material, the susceptibility is less than 0 itself, that means it is in negative term. Okay, or we can say here the susceptibility will lie between -1 to 0. If it is -1, then it will be the perfect diamagnetic material. Okay, so this is what is the susceptibility. Then what about relative permeability? Relative permeability of ferromagnetic material is very large, whereas the relative permeability of a paramagnetic material is more than 1. But here the relative permeability is less than 1. Okay. So this is what is the another difference between paramagnetic, ferromagnetic and diamagnetic material. Okay. Right. Similarly, here what happens, if we will increase the temperature, then the susceptibility will be decreasing. So if we increase the temperature, then susceptibility will start to decrease, and this decrease will be following a very complex manner. Why it will be following complex manner? Because of your hysteresis loop. Okay, we will see the hysteresis loop. The relationship between your B and H will be deciding how the psi value is going to change, and there will be a particular point where the susceptibility will become 0. Okay, or we can say that there will be no effect of your magnetic field on the material. We will see even if it is a ferromagnetic material, and that particular temperature is called as a Curie temperature. Okay, so here what happens, we can say that at Curie temperature, the magnetic property of the material is going to be lost. Okay, whether if it is a paramagnetic material, ferromagnetic material, or diamagnetic material, it is doesn't matter. At a particular temperature, sorry, not that is not right. The correct thing is that ferromagnetic material will only possess the Curie temperature, because the temperature is going to affect its susceptibility. Okay, the temperature for a ferromagnetic material, if we will increase at Curie temperature, the magnetic property of the material will be lost. That means why? Because at higher temperature, the electrons are going to gain more energy, and due to that, the spin of the electron will not be supporting for the property of ferromagnetic material, and it will be lost. Okay, that is what is called as your Curie temperature. What? Curie temperature. But in case of this paramagnetic material, here what happened, as I told you, the psi value is going to decrease, but it is following a complex manner. But in case of your paramagnetic material, we will see the same thing, but the relationship is quite simple, that is they are inversely proportional. If we will increase the temperature, psi value will start to decrease. That is directly proportional. So we can say psi is directly proportional, inversely proportional to temperature. If you will increase the temperature, psi value will decrease. Okay. So that's why here we need not to find any Curie temperature. So there is no necessity of Curie temperature we will find here. Okay. Similarly, for the case of your diamagnetic material, here the susceptibility is independent of temperature. That means whether you are increasing the temperature or decreasing the temperature, there is no effect you will be seeing in this case of your diamagnetic material. That's why here also we will not find any Curie temperature. Okay, we will not find any Curie temperature in case of your diamagnetic material. Then comes is your relationship between B and H. Okay, so in case of your ferromagnetic material, this B and H will show a complex relationship which will lead to your hysteresis loop. Okay, see, all these 3 points are connected to each other. But in case of a paramagnetic material, this B and H will have a linear relationship. So the B and H will be changing linearly. So there is no complex relation will be there. There is no hysteresis loop is there. There is no loss of magnetization will be there. But in case of your ferromagnetic material, we find all these problems. So here what happens, even if it is following this BH curve is following a hysteresis loop, there will be a saturation point. Okay. After that, saturation point means what? There will be the saturation point. What is the saturation point? I will tell you in the hysteresis loop. Okay. There is a saturation point. Similarly, even if there is a linear relationship between B and H in case of paramagnetic material, there is also a saturation point. We will see above that there will be no magnetization we will be seeing. But in case of diamagnetic material, this P and H will be having a linear relationship. But what is the difference between these two relationships? Here the saturation point will be there, but in case of your diamagnetic material, we will not be able to see the saturation point. That means here in case of your hysteresis loop, we find a saturation point. In case of linear relationship of paramagnetic material between B and H, we find saturation point. But in case of diamagnetic material, in linear relationship of B and H, we don't find any saturation point. Okay. So what is the saturation point? What happens now when we are placing a material in a magnetic field, the magnetization is created. Okay, so this is your magnetic field and this is the magnetic induction in the material. So in case of your paramagnetic material, there is a linear relationship, right? Linear relationship means if you increase the value of H, the value of B is going to increase. So it is showing a linear relation. It is the linear relationship, and that linear is going to reach saturation point, after which it is no more going to be stable. Why? Why? Because the spinning is not there. Okay, the dipole moment which is created due to external magnetic field, that will not reach its optimum limit. All the are the same magnetic dipole. That no, 4 electron is maximum value. For here, here in frequency, very in the magnetic field from 0 to value of H, this is not going to increase anymore. Okay, so this is what is the saturation point we say in case of your ferromagnetic material. But as I told you, in case of paramagnetic material, if we decrease the magnetic field again, the same line it will follow, or the same pattern, it will reduce the magnetization in the material. But in case of ferromagnetic material, that particular thing is not available. So when you are increasing the magnetic external intensity like this, reach saturation point. After that, if you decrease the magnetic field, it will follow another path, and even if the magnetic field is removed, the intensity of our magnetization in the material is not going to be It's already ready. Similarly, to remove this retentivity or residual flux, how much negative field you have to apply? Coercive. If you want to get further, you see that the value of magnetization is going to increase. Still, it is going to here also it is going to reach to the saturation level. Here, even if you decrease the H value furthermore, there will be no change in the B we will see. So this is your saturation point. So once it reaches to the saturation point, what we are saying there is no effect of H we will find in the material. Then if we want to remove that negative flux of magnetization from the material, we will start to increase the magnetic field intensity. So if you will increase the magnetic field intensity, we find there is some amount of your residual magnetization remain in the material in the negative direction as well, even if the value of H is equal to 0. So this is also negative retentivity value. If you increase further, we see that when the magnetic field intensity becomes 0, at that time the when the induction value is 0, at that time the magnetic field intensity is not 0, it is having some value. Again, if you increase, it will reach to the saturation point. After this particular point reaching, once it reaches the saturation point, no, it is not going to follow this line anyway. This will follow this loop value. Okay, this loop is that's why it is called as your hysteresis loop, and this is called as your loss, magnetic field loss. Okay, that is what this is what is a BH called for a ferromagnetic material. Ferromagnetic material. You remember that in your branch, this particular okay, this this ferromagnetic material is more important in the point of view of your branch. Okay, because we are going to use this electromagnets at that time. This ferromagnet will come to use, and the property of ferromagnet is going to come to use in case of your application point of view. That's why it is more important to understand this particular thing. I think there is some network issue you find. It might be from my end also. So I will be repeating. One student requested the repeating of this particular hysteresis loop. I will repeat it again in the coming class, next class. Okay. After that, after learning again about this hysteresis loop, we will going to learn about it in about your soft and hard magnetic material and the application, and we will wind up the fourth unit. Okay, so probably tomorrow will be the last class for this unit 4. Okay, after that unit 5 will start. Still, if you people have any doubt related to unit 1 to 4, you can ask me. Okay, so today, as of today, I am not going to take any doubt regarding hysteresis loop, because I am going to take the doubt coming class. Okay, so that's why I am going to end the class over here. If up to your difference between paramagnetic, ferromagnetic and diamagnetic material, if you have any doubt, you can ask. Otherwise, if you need the video link, then you please ping me in the WhatsApp. Okay, you people can leave this meeting and join your calculus class.